we are now recording. Let's go from the current slide. Let's go from the current slide. Not doing anything. Here we go. Okay. Now, I was hoping more people would be here when I made this announcement, but I'll try to remember to announce it again when more come in. You've been at Lawson before, right? Okay. You know that they have student surveys periodically, right? I can remember some summers they didn't do them. And it was sort of puzzling to me today when I saw the email subject, Lawson State Fall 2008 surveys have opened. 2018 surveys have opened. I thought, how have I gotten this far back in my email, you know? And then I looked at the date, no, it was today's date. I went, what? No, yesterday's date. And so I looked, and the message is correct. Students have been notified that their summer 2019 term surveys are available. Please strongly encourage your students to complete the surveys. We value their responses, and we truly do. You know how to log into it and everything. Okay, so your 7-digit student ID number is your login, and then the date of birth is the password. But it's a 8-digit date of birth, 4-digit year. For me, it would be 1951. Yours won't be that long ago. And then month, which is 01 for me, and day, which would be 07 for me. So that's that's your password. And you know how to get to it. Okay, good. Easiest way to get to it is find your email, even though it may have the wrong term and year on it. Find the email, go to it, and you can click right on the thing, and it takes you right there. Anyway, if you'll remind me, I'll tell the others as they come in too. I think I've already marked you present. I did. And any questions for anything so far? Okay. All right. We left off with, in Chapter 12, Matter. We're in Section 12. Does it matter? 12.5, Density, and that's what we're working on now. And example 5 on page 332. Okay? So, ready for that one? A quantity of gasoline weighs 5.50 pounds. So let me get my pen set up. Okay. So they just said weighs, so that's your F sub W, or weight, is equal to 5.50 pounds. Okay. With a weight density, so the D sub W, weight density, of 42.0 pounds per cubic foot. Okay. Find its volume. So what we're looking for is volume. That's the unknown. Now, what formula relates weight density, and volume? And there it just clicked out again. What is this thing doing? Oh, there it clicked back again. I don't know. I might have to go down and see if I can find, well, no, there we're back again. All right. It's a mystery. Okay, what formula relates weight density, and volume? Okay, the weight density, D sub W, is equal to F sub W over volume. Perfect. We're looking for volume, so do you want to solve first and then plug in the numbers, or plug in the numbers and then solve? Doesn't really matter. Plug in the numbers. Okay, well, the weight density, it's flicking again. 42.0 pounds per cubic foot, okay, is equal to the weight, which is 5.50 pounds, divided by volume. That we don't know, okay? So now we've got to solve for V. Either way, you had to solve for V. It's whether you plug first and then solve, or or solve for V and then plug in the numbers. So how do you solve for V here? Second? Okay. Divide which? The weight? Okay, you could, and that will give you an answer, but it'll be 1 over V. And that's really not what you want. You want V. So the good thing to do is get V up in the numerator where we want it. We want V by itself, not 1 over V. We don't like V in the denominator. So let's multiply both sides of the equation by V. You could have done this earlier, but it's okay to do it now. Multiply both sides by V. That wipes it out on the left-hand side. Now what would you do? You're looking for V, so what would you do? You just multiplied both sides by V, so V is multiplied by 42.0 pounds per cubic feet, and over here all you have is 5.50 pounds. You want V by itself, so how do you strip away what's there? How do you undo multiplication? Dividing by what? No. Divide by this. You want to isolate the V.
Okay, so it is.
You divide by the 42.0 pounds per cubic foot. My writing is pretty poor. Divide this side by 42.0 pounds per cubic foot. Okay? Now, over here, all this goes away, and you're left with V. That's exactly what we wanted, because that's what we're looking for. And now on your calculator, divide 5.50 by 42. Or 5.5 divided by 42. Point what? 1 2 what?
It's 130.
130? Okay. Now let's see what units we have. The pounds cancel out, and you have 1 over cubic feet, which you can flip that up and make it cubic feet, which is a very good thing for volume. It's a pretty small number. Now they actually had 0.131 feet. Did yours have the next digit over after the 0, something greater than 4? Greater, yeah. What do you have? Read the digit. 0.13 what? 131. Okay, so we'll make it 0.131. Well, if I'll make it that, if I can get the thing to come up. Okay, it erased too much. Okay, 0.131 cubic feet. And that is the answer they got. Now, they go into a little bit of a practical mode here, which I'm not sure you'll really be all that interested in. But what if you had the density of an irregular solid, just think something like a rock. You can't tell its volume looking at it because it's all jagged and uneven surfaces and all that kind of stuff. It cannot be found directly because of the difficulty of finding its volume. However, we could find the amount of water that the solid displaces, which is the same as the volume of the irregular solid. So they show the picture here. I'm sorry they don't show this on the slide set, but in the figure in the text, 12.27, the volume of the water in the small beaker equals the volume in the rock. So what they do, they've got the beaker there with a hole in the side, okay, and they got the water up to the hole. Now what you actually do, you run enough water, pour enough water in there until it actually comes out, okay? Then you empty the small beaker and put it back under there, and then you very slowly and carefully lower the rock into the beaker and make sure that it gets completely submerged, capturing the water that comes out then, and the same volume of water that comes out of the beaker, that's the volume of the rock, okay? So that's what the next couple of problems are going to be based on. So what we do here is say, I think I'll go to a clean page, all right, to erase this one? Okay. Where is everybody tonight? Okay. Now, they're sometimes a little late getting here, but this is later than normal. So a rock of mass 10.8 kilograms. So the mass of the rock is 10.8 kilograms. Okay? They told us that. Displaces 3200 cubic centimeters of water. So basically, if it displaces that, that's the volume of the rock, is 3200 centimeters. Cubic centimeters. And that first zero is significant. It says, what is the mass density of the rock? So we're looking for density, mass density of the rock. Now what's the formula for mass density of the rock?
Mass density equals mass over volume.
Mass over volume. Okay. Now we almost have that with one little problem. They gave us the volume in cubic centimeters, and I can look at the answer there and tell you they're looking for the density in kilograms per cubic meter. So I like to, at this point, go back and convert the volume of the rock from cubic centimeters to cubic meters. So how would we do that? Conversion factor, two places, equal another blank, and we're trying to get to cubic meters rather than cubic centimeters. This is just a conversion problem, okay? Now, obviously, you started with cubic centimeters. We're ending in cubic meters. So the two blanks there, the first blank is for numbers. The second blank is for units. Which blank do we deal with first? The units. Always put the units in their place first, okay? Now, what unit will go where? One of those must go on top and one must go on bottom. Which one goes where? Make a guess. Which one? I couldn't hear. If you put cubic meters on the bottom, that puts cubic centimeters on the top, and then you multiply this and you get centimeters to the 6th power per meter to the 3rd power. Ew.
Wait, so
messy.
CM3 on the bottom?
Okay, yeah, the centimeters.
I was thinking that stand for cubic meters. So
Okay, so let's reverse these. Now, I'm also going to take off the 3's because I find it easier to deal with just the unit first and then we'll cube it. So we'll put centimeters on the bottom, meters on top. But before we do anything else, I need to find where I buried your stuff. There it is. Okay. And I must say, this is just about the best class I've ever had about getting in your test on time. Okay? Seems like the first test, all 4 of you had it in pretty quickly, and the second test, you had in pretty quickly. So, now, of course, it's one of the smallest classes I've ever taught, with only 4 people, but still, it's good that you all are getting it in on time. Okay? The second thing And you probably have received this email, but it probably had a title that made you say, that's not for me. It is for you. The one they sent us yesterday, but I didn't see it until today, the title of it, the subject was, Lawson State Fall 2018 Surveys Have Opened. And I went, what? Fall 2018 was almost a year ago. Why are they sending me this now? Am I in the middle of old emails or something? I looked at the date and said, no, it's July 2019. So I opened the email to look, and sure enough, they said students have been notified that their summer 2019 term surveys are available. Have you been here before that you know about doing class surveys? Okay. Please do the student course evaluations. These are very, very crucial to us. To me personally, I take great, I pay close attention to what students are saying. In a composite sense, I will never be able to know what you put down. Never. And I don't want to, okay? Because what they do, they don't let us see anything until a good number of students have done it. So I imagine when all 4 of you have done it, then I'll see the composite. I never see the individual. So don't ever feel threatened that, oh, he'll see what I said and he won't gonna like this, or she'll see what I said. And no, we'll never know, okay? What we see is the composite. And that's what's important, okay? I had one adjunct instructor who's a pretty good instructor, but he had either 1 or 2 small classes. I think it was last fall when he taught, but he didn't encourage the students to do the student course evaluation. I think he only had like 13 students. So he didn't encourage them to do the student course evaluations, but 1 or 2 students got really mad at him. I don't know why. They either didn't get a grade they wanted or something like that. So those 1 or 2 students filled out the course evaluations on him and gave him really low scores. So when I went to do his evaluation this year, I had to put down those low scores on his evaluation. And when I met with him last week, I said, look, I have a feeling I know what's going on here, but this is what I had to put down. He looked at it and said, well, you know this isn't trust that. I've observed you teach, and I don't see it either, but I haven't observed you this year. This is what the students say, I have to do it. And they gave him some pretty low scores, some 1s and 2s rather than 3s, 4s, and 5s. And but it wasn't enough to hurt him. It just gave him a bad. I say, the lesson learned here should be encourage all of your students to do the course evaluation, because the odds are the ones that are disgruntled with you are going to do them. It's the ones that are pleased with you, they apathetic and won't mess with it. Encourage them to do the student course evaluation, because I've evaluated him year after year after year. He's always gotten good marks from the students. This year, only 2 students responded, so he got some pretty low evaluations. Not that it makes any big difference, okay, but it does matter. So please do the student course evaluation. All right, and I don't know how long they'll be. Oh, they'll be open till the 8th of, there she is, until the 8th of August. So you've got plenty of time, but just don't forget. The term's going to be over way before the 8th of August, so don't put it off till then. You'll be forgetting about all summer, so do it. Now, do you know how to access them?
Yeah.
You do? Okay, well, I'm talking about student course evaluations. Okay, they're open now. Check your emails, and if it has the wrong subject like it did on mine, it said Lawson State Fall 2018 surveys have opened. This is summer 2019. I was just about to delete it until I opened it and looked and saw they just copied an email, but they forgot to change the title, okay, the subject line. They changed it in the body, but didn't change it in the subject. So please check that. Have you done student course evaluations here before?
Long time.
Okay. If you go to the email, it tells you exactly what to do. Okay, so go to the email to see it. I'll give you a brief on how to do it. Your login to do the emails is your 7-digit ID number. 7 numeric digits. Probably starting with 22 something, or maybe for you once, if you've been here a long time ago, they may use your old number. But anyway, whatever your student ID number is, 7 digits. Then your password is your birth date, but it's given all numerically. 8 digits. The first 4 digits are the year of your birth. For me, it would be 1951. It won't be that long for y'all, okay? Then the next 2 digits are the month of your birth. For me, January would be 01. Do 2 digits. And then the last 2 digits are the date of your birth, and that would be, for me, 07. Always, if it's a single digit, put a 0 in front. All right. Now, if you want to know the easiest way to access the Smarty Valves, that's what it's called, find the email. Go to the email, and they have the link right here. Click on the link, it takes you right there. Okay? That's the easiest way. If you don't have the email or don't know how to access your email, what you can do is go to the Lawson State web page. When you go to the web page, the home page of the web, you know, there's a bunch of blue tabs at the top of the page. But over near the right, there's a big gold tab, and it says Quick Links. Click on the Quick Links, and then you'll get a whole huge menu, and you'll have to scroll down, and you look for I think the title of the area is Surveys. So click on Surveys, and it'll take you to the place. So much easier to find it on the email. Just click on the link, and it takes you right there. Okay. So it'll be open from now, actually yesterday, until the 8th of August, which will be several days after the term is over. But don't wait that long. You'll forget about it, okay? I know when I was a student, especially an undergraduate student, the day I turned in that last final, my mind clicked off and I was heading home, whether I was going home or not. If I waited until then to do the survey, I never would have, okay? Do it while you're thinking of it, okay? Y'all are probably far better organized and planning and everything than I was. But boy, by the time that term was over, I was ready to go home. And I was saying also that this is the very best class I think I've ever had about getting tests in on time. And here's your second test. And if you have any questions about any of them, I'll be glad to work them. Because everybody's turned them in, so I can do that. Okay. Still waiting for Brianna. If she gets here, I'll give her hers. All right. We were doing example 6 on page 333 in chapter 12, matter, and we're in section 12.5, density. And so that's what we're dealing with here is density. And periodically my projector's been checking out on me, but it's held steady for a while. Example 6 on page 333 said a rock of mass density, or any questions before we get back to this? Any questions? Okay.
On that test.
Huh?
On that test.
If you got them, yeah, anywhere.
That you just gave us, I can do it after class.
Okay.
Go ahead.
Okay. Well, I'll be glad to do it anytime. Okay. Or any other questions anywhere.
333.
Yeah. Oh, and by the way, also, while I'm thinking of this too, you weren't here last time, and we were close enough to the end of the chapter. I asked if y'all wanted to go on and get your third test, and everybody said yes. So I passed out the third test, but you weren't here, so let me give this to you before I forget to.
Sean sent me one, but I printed it.
Oh, you
It was
did?
so dark,
Yeah.
I couldn't see it.
Okay.
Thank
So
you.
there's one especially for you there. Light enough to read. Okay. All right. Back to example 6. And while the example reads is a rock of mass 10.8 kilograms, so we wrote that down, the mass of the rock was 10.8 kilograms, displaces 3,200 cubic centimeters of water. So that's the volume of the rock. It's the volume of the water, but it displaces that much, so that's also the volume of the rock. What is the mass density of the rock? Well, we know that formula is the mass density is equal to mass divided by volume. The trouble is mass density is usually given in kilograms per cubic meter, not kilograms per cubic centimeter. Okay? I actually prefer grams per cubic centimeter, but this book doesn't, so we're going to do it. So what we had decided, Krishana and I had decided we needed to do our unit conversion. So we wanted to change the 3,200 cubic centimeters to cubic meters up there. The book liked to do the calculations and then do the change, and I found it just really awkward to do it that way. Let's go on and change it to cubic meters up there. And we just put in our two blanks for the conversion factor and then a blank for the number of cubic meters. And we decided always put the units in their place first, so we filled in the units, though we messed around with them a little bit. But you see, you got to put centimeters on the bottom, so they will cancel out, meters on the top, because that's where you want them to be, on top. Okay? So, now we fill in the numbers. Now that we got the units in the place, how many meters in a centimeter or how many centimeters in a meter? That you do need to know. How many meters in a centimeter or how many centimeters in a meter? All right, I go to my handy dandy little, oh man. I have to watch this. My cord periodically unlinks. What's this called? Everybody see it? Say again. A penny. How much is it worth?
1 cent.
1 cent. What part of a dollar is that? In other words, how many cents makes up a dollar?
50.01.
Okay, that's how many dollars a cent would be. So how many pennies would make a dollar? 100. So you can do it either way you want to. Centi means 100. So you can either put the 100 down here or put the 0.01 up there. I don't care. Which way do you want to do it?
100 on the bottom.
Second? 100 on the bottom. I like that too. Okay? I said I didn't care, but I do. No, I'm just kidding. Okay. So 1 meter is 100 centimeters. That works. Except we don't have meters and centimeters. We have cubic meters and cubic centimeters. So that means we got to cube the units. That means we also cube the numbers. Okay. Now, I can cube 1. 1 times 1 is 1 times 1 is 1. That's easy. It's that 100 that we need to cube. 100 times 100 is 10,000 times another 100 is 1,000,000. So that's 1 with 6 zeros. One more. Okay. That's how many cubic centimeters are in 1 cubic meter. Whoa. Okay. So what we've got to do is move this decimal 6 places to the left to divide this by 1,000,000. So that would be 1, 2, 3, 4, 5, 6. So that would be 0.00320. Okay? Because that first, the 0 after the 2 is significant. That's why the bar is up there. So we include it here. 0.00. Those two aren't significant. They're just placeholders. 320. That last one is significant. Cubic meters. So that's what we put here. So the mass is 10.8 kilograms divided by 0.00320 cubic centimeters. No, cubic meters. Okay, sorry. Went to all that trouble and I was going to ignore it. Okay. Cubic meters. I don't know how long my plug was out, but my computer is now making these silly little noises at me. All right, you need to plug that into your calculator and see what you get. A pretty big number, by the way, because you can move this decimal 4 more places back to the right, move this decimal 4 places to the right, and that would give you 32. You don't have to move them 4. It doesn't matter. Your calculator will take care of it. But what do you get when you divide 10.8 by 0.0032? I think I would have just moved it 3 places right. Put it right there. And that would be 3 something something something. About 3,000? 3,375, and that would be kilogram per cubic meters. Okay? The only trouble is we only have 3 significant digits, so this is approximately 3380 kilogram per cubic meter. Now let's see what the book got. Ah! That's what they got too. You round it off because all your digits, the mass is in 3 digits, your volume in cubic centimeters is 320, with the first one having a bar, the second one not, 3 significant digits. Of course, your conversion factors are as many digits as you need, so your answer can't be any more significant digits than you had to start with. You had 3 and 3 to start with, so round that to 3. And what I'd say to do is count 1, 2, 3, look to the right, that's 5 or more, up that by 1 and make that one 0. 3,380 approximately kilogram per cubic meter. And that's what they got to. This computer does weird things. Over the long 4th of July weekend, I had not waited till my last class on Wednesday had uploaded before I went home, and I just never had a chance to take it out because we left and went straight to the lake over the weekend, and then we worked the whole weekend, so I never got it out and charged it. And when I came into work Monday morning and went to set up, the battery light was on. And I taught for more, or had the computer on for more than 9 hours, and the battery light stayed on the whole 9 hours. So, oh man, my battery is just about dead, I think. So I took it home that night, and I was going to charge it overnight. So I plugged it in, did a few other things, and in 15 minutes the battery light went off. So I don't know. It does really strange things. So it's up here making noises at me now because it does strange things. Okay, any questions on example 6? All right, clear the slide? Okay. Example 7. A rock displaces 3.00 gallons of water. So this is one expression of the volume of the water, okay, is 3.00 gallons. But that's also the volume of the rock, okay, because the amount of water it displaces is the amount. Now that's a pretty impressive rock that it's to 3 decimal places, 3.00 gallons of water. It has a weight density, that's D sub W, of 156 pounds per cubic foot. 156 pounds per cubic foot. Okay? The question is, what is its weight? We're looking for F sub W, the weight of the rock. That's the unknown here. Now, ooh, that is not good. I put for gallons, I put G. G is not the abbreviation for gallons. G is the abbreviation for grams. Volumes can't be in grams. That's gallons. So GAL is gallons. Okay. She's a good old gal. You know, never mind. Okay. So that's the volume. Does anyone see a problem with this? Usually at this point, if you see a problem that has to do with the units. Any problem with the units? Volume up there is in gallons, and your weight density is given in pounds per cubic feet. So what we need to do is convert our gallons to cubic feet. Okay, might as well go on and do it now. Don't wait till later in the game and do it like the book does, okay? Or you can. There's nothing wrong with doing it the way the book does. I just think it makes more sense here. Okay? Now, what we're dealing with is a volume conversion. So go to the back of your book in Appendix C, your tables, and we're looking for a conversion table for volume. Table 1 is just U.S. weights and measures. That's not what we need. Table 2 is conversion table for length. That's not what we need. Table 3 is conversion table for area. That's not what we need. But Table 4 is conversion table for volume. So we want something that will convert gallons to cubic feet. And by the way, before we do anything else, let's decide where we're going to put our units. Ha! We got perfect attendance again tonight. Good deal. And by the way, I forgot to mark the last 3 people who came in. Brianna's here. Haley's here. And Sharon is here. Okay. And I also have for you, Brianna, as a special gift for coming in tonight, because this class is the best ever at getting your test in on time. Here's your second test. I have to haul these around all term. I do on some classes, but not in this one. Okay. Now, the other thing, and poor Krishana has heard this now 3 times. She'll hear it, no, twice. She'll hear it the 3rd time. Brianna, you should have gotten an email. It may have had the wrong subject line on it. The one they sent to us had the wrong subject line. It said, Lawson State Fall 2018 surveys are now have opened.
Yeah, I seen it.
You saw it?
I go on both of my emails daily.
Okay. Did they correct it on yours?
Oh, yes, sir. On the,
They did. Okay. Okay. So you already know about it?
Yes, sir.
Have you already done them?
Yes, sir.
Really? That's amazing. Huh?
I did when it came.
When it
check my
came.
emails daily.
Okay, good deal. So you don't have to do it that fast, but you can if you want to. You can wait till the end of the term if you want to, but just don't wait past the 8th of August. They're going to shut it down then. So please do the student course evaluations. Did you have any problem accessing it?
No. I went straight to it.
Yeah. If you
link.
click on the link, that's the easiest way to do it. Go to your email, and there's actually 2 of them, one with the correct subject line and one with the wrong subject line, right? Yeah, so both of them have the correct thing on it. Good deal. Because I saw Miss Glass this morning, and I told her, guess what I saw? She said, whoops. Okay. So we were talking about, and now I've lost my place because I did that. So let me go back to the table in the back. Here's my marker. I need something to hold my place in the front too. To table 4 in the back, and we're going to convert the volume from gallons to cubic feet. So what unit is going to go where? One has to go on top, one on bottom. Which one goes where? You tell me. Always put the units in their place. The first blank here, that's for the numbers. Don't worry about that yet. Put the units in their place. Which unit goes where? Let me know. between gallons and cubic feet. One goes on top, one goes on bottom. Which goes where? Which one? Gallons on the bottom. You're absolutely right. That puts cubic feet on top. And why is that right? Because the gallons will cancel out now, and you're left with cubic feet just where you want them. Okay? Now, we need to match numbers with the units. So that's why you go to Table 4 in the back of the book on page 687 and see if we can find numbers to put into place. Okay? So here we have at the bottom of Table 4, just before you get to Table 5, it has 1 U.S. gallon equals, we know that, 4 U.S. fluid quarts, 8 U.S. pints, 128 U.S. fluid ounces, 231 cubic inches, who cares about that, or 0.134 cubic feet. So there we can put 1 gallon, because that's where you started, is equal to 0.134 cubic feet. 0.134 cubic feet. See, once you get the units into place, all you do is match the numbers with the units. Did everybody see how we did that? Find it in the table, saw how to do it? Okay. Then pull out your calculators. Or you don't even need a calculator on this one. You can do this one basically in your head. 3 times 0.134. 3 times 4 would be 12. Carry a 1. 3 times 3 is 9. Carry the 1 would be 10. Carry another 1. 3 times 1 is 3. That 1 you carried is going to be 4. And this is a decimal right there. Okay? 0.402 cubic feet. All right. We got that part done. Now, how do we find our weight? That's what the question is. What formula relates volume, weight density, and weight? What's the formula that does that? Anyone know? What formula relates volume, weight density, and weight? Does anyone happen to remember?
Is it the density of weight equals
dW is equal to what? FW over V. Perfect, perfect, perfect. But we're looking for FW. So that means we want to isolate this. How do we go about isolating that? I don't want it divided by V. I want it by itself. So how do you undo division? Multiply both sides of the equation by V. Okay? And here the V's cancel out, which is exactly what we wanted them to do. And that leaves you this. So we know that force due to weight, or weight, is equal to density, weight density times volume. And we know our weight density is 156 pounds. See, it's doing that again. And just oh, there it's come back. Okay. I don't know. Maybe it's a projector. I don't know. I think it's the cable, because this is the first time I've used this cable in a long time, and it used to work really well, but it's not working as well tonight. 156 pounds per cubic foot, okay, times the volume, which is, use this one here, 0.402 cubic feet. Okay? So what would be the weight? Notice here the units cancel out, cubic feet and cubic feet. That leaves you with pounds. An excellent, excellent unit for weight. 156 times 0.402. I won't do that one in my head. I'll let you. It's not that hard, but what you get? I could probably do it. You want me to? That's 312 and double that, 624. Add that together, you get 62712, and that's a total of 3 decimal places. 62.7? Is that what you get?
Yeah.
Okay. You see, calculators slow you down, don't they? So that's 62.7. I don't need those other 2 digits. Count off 3, the thing to the right, and that would be in what units? Pounds. 62.7 pounds. So let's go back to our whatchamacallit and see what we got. Turn the page. This is example 7, the bottom of the page. And that gave us 62.6 is what they got. Well, they went to great lengths to screw things up. I bet you they just round off too soon. But if you're within that much, no problem. All right. So you see, the book sometimes doesn't have quite the right answer either. I think I did mine right. Okay. Now, sometimes we really don't care about this exact density of something. We want to compare densities of 2 materials, so we compare them with the density of water. Water is the most common substance on the surface of the planet, so they use that. So they give a special name to that comparison, and that's called specific gravity. That's a rather strange name because gravity is gravity, but they call this specific gravity. They abbreviate it SPGR with a space in between. Okay? And here's what the definition of specific gravity is: the the density of the material divided by the density of water. And we know what the density of water is. I know. I'm going to wait. This time it didn't come back on. Boo hiss. I had to do this. Now it did. Okay. It has a mind of its own, and it's a sick, sick mind. Okay. Now, the density of the material divided by the density of water. Now we know what the density of water is. If you go to the table that is a few pages earlier, back on page 330, liquids, when you see water, the mass density of water is 1.000 grams per cubic centimeter, or 1,000 kilograms per cubic meter. Really easy to remember that one. Your weight density is 62.4 pounds per cubic feet. That's the density of water, okay, in either unit. And here's the beauty of specific gravity. You could be talking about weight density, which has a different number than SI unit density, okay, than mass density. But if you do specific gravity, that all disappears and it's one number. So it doesn't have any units. It's not different for weight density or mass density. It's the same. Specific gravity is the same for your material. It doesn't matter which density you use, as long as you use the same density when you make the conversion. Okay? So let me see where we are here. Here we go. So let's do a few problems with specific gravity. Okay? I think I'll go to a new slide. Anyone need this a little longer? You okay? And by the way, does anyone need a light on? Krishana said she didn't care. I get plenty of light here, but I don't know if you do. Y'all are a little bit in the dark. Do you need light? You okay? All right. So I'll erase all this ink. And it tells us the density of iron. And you have to look at the units. This will be mass density of iron. Fe stands for iron. just hopefully will come back, is 7,830 kilograms per cubic meter. 7,830 kilograms per cubic meter. What a big number, what an awkward number, but that's what they use, and they use SI units. Okay? It says find its specific gravity. And remember the thing is SPGR with a space in between. So what formula gives us specific gravity? I'm sorry, this is just going not crazy. Okay, is it going to come back? What I'm beginning to wonder is, because when I'm writing on the screen it tends to do it, or when I move something, so I'm wondering if there's a short somewhere in there, and so I don't know. What's the formula for specific gravity? Just gave it. I'll erase the screen. Maybe I should have left it. It's the density of the material, which this happens to be iron, divided by the density of water. Okay. Now, since we were using, that should not have a slash through the O. That's not a 0, that's an O. Okay, H2O. Okay. All right. Since we're using mass density for iron, this is driving me nuts. The whole computer is being so weird tonight. Still not coming back. Okay. Tell me when it comes back and I'll quit what I'm doing. Back? Okay. Let's see if this will lay down. And when that did that, my cord came up. Okay, I've got my cord back and projectors back. This is just doing weird things. All right, since we use the mass density of iron, we need to use the mass density of water. So we know the mass density of iron, they gave it to us. 7,830 kilograms per cubic meter. Okay, big old number there. But what was our mass density of water? Just gave it to you a few seconds ago. 1,000 kilograms per cubic meter. And that's why it's useful to put the units down. If you had used the one for pounds per cubic feet, you say, hey, you can't do that. You can't divide kilograms per cubic meter by pounds per cubic feet. Gets you to do the same one. And notice the units disappear completely. And it's real easy to divide by 1,000. You just move your decimal 3 places to the left. So the specific gravity of iron is 7.83. No units. 7.83. And that's true whether you're talking about pounds of iron, grams of iron, kilograms of iron, cubic centimeters of iron, cubic feet of iron. It doesn't matter. If you use the same densities and do the division, you get the same specific gravity. That's what makes it such a useful number. And that's what they got in the book too. That means that iron is 7.83, almost 8 times as dense as water, thus it sinks. Okay. So let's do example 9. You think we have room on this page? I think so. Here it says the density of oil, is 54 64.2. And when I saw that number, I knew that had to be in pounds per cubic foot. Okay? Now, which kind of density is that? It's not mass density, it's weight density, because pounds measures weight. Okay? Now it says find its specific gravity. So the specific gravity for this particular oil here is going to be the density of the oil divided by what? Density of water. Okay? But which density do we use? We know what we use of oil, 54.2 pounds per cubic foot. What density do we use for water? 62.4. Is that what you said? 62.4 pounds per cubic foot. Okay? Okay? You go back to the table a few pages earlier. Okay? Page 330. And, okay, there's two parts to answer your question. First, you go to the table, but then you go to the right density. Since the oil was given in pounds per cubic feet, you go to water in pounds per cubic feet, which is 62.4. And maybe after a while, you'll say, oh, I know that. I don't have to look at the table anymore. But I always look at the table because I have a good memory. It's just short, so I don't trust it. So if someone has a calculator, divide 54.2 divided by 62.4. I think you'll get 0. Is that 9 or 8? 54.2 divided by 62.4. 0.869. 3 digits? Do we have 3 digits? What units? None. The units cancel out. That's why you use the same units for both. Let's see what they got. 0.869. Good for them. Okay? And what that means is that oil is only almost 0.9 times as dense as water, meaning it floats on water. And you know, remember when they had the Gulf oil spill? That oil was coming to the surface, and it may still be coming to the surface because some of it gets trapped down below. And but when that happened, boy, the beaches were in really bad shape because that oil came up there. Not every beach, but a lot of beaches got hit by the oil. So they had booms and rigs and all sorts of things out there trying to keep those beautiful beaches beautiful. All right. Now, in general, the specific gravity of water is what? Okay? The specific density of a material denser than water is going to be greater than 1. And a material that's less dense than water is going to be less than 1. Okay? Those with a specific gravity less than 1 are going to float in water. Those with a specific gravity greater than 1 are going to sink in water. And one of the devices they use, and you may have seen this, it's called a hydrometer. Basically, it's measuring. Meter means to measure. Hydro means water. You're measuring the density of a water. Now, quite often this is not just drinking water or something like that. You certainly hope not. You might use it for your battery water to see if your battery has enough electrolyte in it. And so that's what they show in pictures here. And they have a few more tables. Specific gravities for a lead storage battery. A new fully charged battery will have a specific gravity around 1.3, but if it's old and is totally discharged, it's going to be almost like water, 1.15. So if your hydrometer gives you too low of reading, it's time to change your battery. You also use this for antifreeze, okay? If you have temperatures that are going to get down only a degree or 2 Celsius below freezing, you can use antifreeze. You can have just pure water in there, 1.00. But if you get down as much as 3 degrees below freezing in Celsius, then you need 1.01, and it goes on up from there. If you're getting as cold as 51 degrees below freezing, and by the way, and this is Celsius, the coldest I think I've ever seen it here in the South, we were down in single digits on Fahrenheit, which would probably be pretty close to the 19.82 in Celsius, and that you would have had to have specific gravity of your radiator water to be about 1.05 then. Okay, so that's why we use specific gravities when you're measuring things like your battery water or your radiator water. And then there's some others, common materials. Benzene, can't remember exactly what it's used for. It's an organic compound, but it's about 0.9. Ethyl alcohol, you know what that's used for. That's, astringent. It's about 0.79. Gasoline is about 0.68. Kerosene is denser. It's about 0.82. Mercury, way denser, 13.6. Seawater is about 1.025. Sulfuric acid about 1.84. And by the way, that is the electrolyte in your car batteries, is sulfuric acid. So you don't need a whole lot of that to get your density. Remember, they said they want it to be about 1.30. So you need a certain amount of sulfuric acid, but a lot of that is water. Turpentine about 0.87. Not many people use that much anymore. It's close to kerosene. And water, of course, is 1.000. Okay. All right. Homework exercises here in 12.5 include any of the odds 1 through 7, any of the odds 9 through 23, any of the odds 25 through 29, any of the odds 31 through 33, and try to do either 35 or 37. 35 is not all that practical, but it may be an interesting thing for you to do. Okay? There is a glossary here if you need to bone up on any of the words we talked about. It's not really that important in this class, in this section. The formulas given on page 339 are pretty good. There's the stress formula. Stress is force per unit area. You can also think of that as pressure is force per unit area. The Hooke's law constant is force, and it's not just Hooke's law, but it's the elasticity law. The amount of force to change of displacement is force divided by delta L is your spring or elasticity constant. And then your density formula is mass density is mass per unit volume, weight density is weight per unit volume. And then specific gravity is density of material divided by density of water. The review questions may be of interest to you just to make sure you have the concepts right, but the more important thing are the review problems, and there you could do any of the odds 1 through 19, because those are in the back of the book. Now, there's some applied concepts there. You don't need to do those, but if you wanted to do them just for fun, you certainly can. Okay? Now, no reason to do chapter 13. That's on fluids, so we're going to skip 13. 14 is temperature and heat. I don't think you'll have need for that in diagnostic medical sonography, so we're skipping 14. 15 is properties of gases. We had properties of solids and liquids in that last chapter. We didn't do properties of gases. I don't think you need that in what you're doing, so we're going to skip that one. But chapter 16 is where we pick up again, and this is wave motion and sound. And that's exactly what y'all are dealing with in diagnostic sonography, medical sonography. So this is maybe one of the most important chapters here. Now, a lot of this is going to be talking about the physics of sound, but that's still important for you to know. You'll get in onto the sonography part when you get into those courses. But this is just talking about wave motions and sound, and I imagine she's going to, whoever your instructor is going to expect you to understand enough of the physics to get by. So, all right, for me to erase, why did that happen? Okay, erase this ink, all right? You need that anymore? Okay, last two problems there. So erase the ink and go on to chapter 16. All of you have your test on 12 now. All right, we've got about 15 minutes left, so let's see what we can do here. We're first going to talk about the characteristics of waves. Now, there's lots and lots and lots and lots of kinds of waves. You're probably used to water waves, and that's a good way to think of waves, and we're going to use those a lot. But you see, sound is also waves. If you put your hand in front of your mouth while you're talking, you'll feel little spurts of air coming out. Hopefully not spit. I try not to spit, but you'll find little things. Well, the way that the sound gets from my mouth to your ears is by compression waves of air molecules. And it's pretty amazing that your ears are sensitive enough that they pick up, even this distance away, those little, you can't feel that pressure difference, but your ear does, your eardrum does, and it's accentuated by the other things in your ear. Your ear is an amazing, amazing instrument, just like your eyes are just absolutely phenomenal. Your brain that processes all that is really amazing. We are really amazing machines, our bodies, okay? Some more amazing than others, okay? So we're talking about the characteristic of waves, because what does a wave do? Energy may be transferred by the motion of particles, okay? Sound energy is moved by the motion of air particles, okay? Water waves carried by the motion of the water particles. Electricity is carried by electromagnetic waves. You can't even see them. There's not even any substance there. They say here the motion of electrons, which is sort of true. Heat is conducted by the motion of atoms and molecules. Tides and winds, example of transmission by motion of fluids. Energy may also be transferred by wave motion. That's what we're going to be talking about. That's what y'all are going to be dealing with in diagnostic medical sonography. The sun's energy is transported through space, nothing out there, okay? It's transmitted by electromagnetic radiation, which can be very deadly if it's in the form of gamma radiation. It can be life-saving if it's in form of light, visible light energy. Heat is another form of electromagnetic radiation. It's just really amazing. Radio waves are another illustration of electromagnetic radiation. They carry the energy of communications. That's what your cell phones, that's what my computer, when I go to upload it to YouTube, it's all being sent by electromagnetic radiation, okay, which is waves, okay? And sound waves are just another type of energy being transmitted through the movement of molecules, okay? So let's put a couple definitions here. How in the world I get this wrapped up so badly every time? Okay. A wave is a disturbance okay? A disturbance that moves through a medium goodness gracious, I can't write. And you're saying, tell me about it. Okay. Or through space. It doesn't even have to be a medium. Or space. Okay. Sound energy requires a medium. Okay. In this room, it happens to be air. Believe it or not, those little air particles are getting what they call compressed and rarefacted every time I speak. Every time you speak. And that's what your eardrums are picking up. And that's what sonography is, picking up that disturbance in the medium. If we're talking about electromagnetic radiation, no medium required. In fact, medium gets in the way. That goes through space. Okay? There can be medium there, but it's not helpful. Okay? Now, that displacement of atoms away from the equilibrium or rest position in an elastic medium, we talked about that before, that's what sends the pulse. Okay? Let me go back. I don't think, all right, to delete this one. I'm going to go to see where we pick up on our slide set. Okay? It's not a very impressive slide set. Okay, but let's go to it. All right, Chapter 16, Wave Motion and Sound. We're not quite there yet. We're close, but not quite there. Let's go back and get our these definitions in place. But what I was hoping they'd have, but they don't, is this. Now, not everybody has a book, so I'll try to hold this up so you can see it. It doesn't get projected, so it won't be picked up on the recording. But here we have a series of balls connected by springs. If you were to flick one of those balls, like ball number B, maybe flick it to the right, flick it to the right, flick it to the left, or even up or down, something like that, you'll see that the other balls sense that. The disturbance happens in the medium. The medium here is a system of balls and springs. And all of them will start jiggling around then. Okay? So that is an example of a wave. Now, what I described was a pretty chaotic wave, but it is a wave. But if particle A was forced to oscillate about its equilibrium position, it's going to affect the spring in between A and B. So B starts oscillating, and then C starts oscillating, and then D starts oscillating, and E will start oscillating too. Maybe not as strongly as A is, but they'll all sense it over time. Okay? Now, we're going to get to 6.2 in a minute, but let me get some of these terms first. Okay? I said 16.2. Okay, let's hit some of the terms. Number one, or the first one they have is not highlighted, bold-faced, is a pulse. Oops, let me get my pen back. Okay, a pulse. Now, this isn't taking someone's pulse, though that's very similar to what we're talking about, okay? This is a non-repeated disturbance. See, we hope when we take someone's pulse it is repeated. Non-repeated disturbance. That's like the flicking of the ball, okay? That would be a pulse. Non-repeated disturbance that carries energy. There's the key. That carries energy. Okay? through the medium or space depends on what kind of wave you're talking about. If it's a sound wave, it's through a medium. If it's electromagnetic wave, it's space. So it's either a medium or space, one or the other, depends on the type of wave that you have through space. Now, if that pulse is repeated periodically, then a series of crests and troughs will travel through the medium. Now, what do we mean by crests or troughs? Think of putting your hand in front of your mouth, and when you feel that pulse of air, that's the crest. When you don't feel it, it's probably a trough. A crest is an uptick, a trough is a down kick, okay? And I guess that's a good place to go back to our other. So I'm going to lose this when I do it, but y'all got this? Okay. So let's go back to the slide that we left off with. So we weren't quite ready for it, but we are now, I think. Okay. Here's an example. Now, I'm going to digress just a little bit. I can remember when I was a little boy and we were doing something out in the yard, maybe watering the garden or something like that. We had a hose stretched out across the ground. I got such a kick out of picking up the end of the hose and yanking it upward and yanking it back down as hard as I could. Now, what happened when I did that?
Wave.
Yes, you saw the wave travel down the hose. Now, it didn't travel as fast and furious as I did it, but you would see it do that. And I was just fascinated by that. This is what's being described there. The amount of displacement I did with that hose, that created a crest. And when I brought it back down, that created a trough. Okay? And then the hose continued carrying the energy that I had expended. I didn't know at the time that's what it was doing. When I picked it up and lowered it down, it carried that energy down the hose. So if the hose had been a perfectly elastic medium, the crest would have been the same on down here, the next trough is the same, the next crest the same, the next trough the same. Of course, it wasn't an elastic medium, and it sort of petered out after a while. Okay? But you'll notice here the displacement of the particles are up and down, but the energy is left to right. You see that? The direction of the wave travel is this way, but the displacement of the actual particles were up and down. I went up and down, but the energy went out into the yard. Okay? That is one specific type of wave that's called a transverse wave. When I'm talking to you and these pulses of air are leaving my mouth and going to your eardrum, it's not the same air. It sends it through the medium. But when that happens, that's what they call a longitudinal wave. Because then the movement of the particles is in the same direction as the direction of the wave travel. So this is called the transverse wave. The other is called a longitudinal wave. Sound waves are longitudinal waves. Hoses on the ground are transverse waves. There are other types of transverse waves as well. Okay? Now, so this is a description of a transverse wave. I'll give what it says: a displacement in a medium. Let me get my pen back. Displacement of a medium. Okay? Writing stinks. In which the motion of the particles is perpendicular to the direction of the wave motion. goodness, I can't write. Perpendicular to displacement of material particles. Wait. No, wave travel. I already said, sorry. Get my eraser. It's perpendicular to the direction of wave motion. Okay, straight out of the book, pretty much. Okay. And that was the figure we see here. Okay. Now, let's talk a little bit about some of the characteristics of the wave. The first of these is called the amplitude of the wave. Okay, amplitude. It's the maximum displacement of any part of the wave from the equilibrium or rest position. Maximum displacement of any part of the wave from the equilibrium or rest position. Okay. This is the rest position. Okay, right here. The line right through the middle. That's the rest position. Here you see the displacement of particles perpendicular, meaning right angle to the direction of the wave travel. And this would be the amplitude, or this would be the amplitude, or this would be the amplitude. The maximum displacement of the particles from the rest position, from that equilibrium line there. Okay? That's what we call the amplitude. So, if I can find my chair, I'll sit back down. And this is the amplitude here. The maximum displacement of a particle from the equilibrium or rest position. Easy to see on transverse waves. Not quite as easy to see on your longitudinal waves. Okay? And I'm afraid we're just about out of time, aren't we? Is that right? Okay. So what we'll do, we'll pick up next time with longitudinal wave. Okay? And that will be this next slide here. Okay? So we'll pick this up next time. All right. I don't think we got far enough to have any homework assignment in Chapter 16, but you can continue working on the problems in 12 and on the test in 12. And that should keep you busy for a little bit, right? Now, when I gave you those tests, and I didn't say this, Sharon, I probably should have, that test I gave you, especially the one that you got that was so dark, and the one I just gave you should be more obvious. On number 3, I don't know what the deal is with whoever writes these things. They really blew it. That's supposed to be, on the first line of number 3, 50,000 pounds. They put 50, 00 pounds. It's always got to be 3 zeros. They left off the 0, and then on the B part of the question, what would be the compression of, what would the compression be if the weight were 60,000 pounds? They left off the 0 there too. So those have extra zeros, that one extra 0, and that's what I tried to draw in. But if you think I just was messing up the page, it was supposed to be a 0 there. 50,000 pounds and then 60,000 pounds. Number 5.
Find the volume of silver.
Okay. A cylindrical piece of aluminum is 6 centimeters tall, 6.00 centimeters tall, 2.00 centimeters in radius. How much does it weigh? Okay? Now, there's several parts there. What is a cylindrical piece of aluminum? Okay? Well, it doesn't matter what cylindrical means, but what is a cylinder? And I'm trying to remember now, was it front of the book or back of the book? Ah, there it is. Back of the book, back inside table, that is a picture of a cylinder, the little orange one there. That's at the back inside cover of the book. It doesn't have a page number. Go to the very back hard cover of the book, open it up, it's on the paper page right across from that. Okay? I've got to find it again. A cylindrical piece of aluminum, 6 centimeters tall. On this picture, that would be the H, the height. Okay? And 2 centimeters in radius, that would be the little R you see there. Okay? Now, what is it talking about? How much does it weigh? Obviously, we need to know, okay, a couple things. You're in the SI units, so then you'll be using the mass density. So what you'll use is a volume formula here, and that's V is equal to pi r squared h, where pi is the number pi, 3.1416, but it's on your calculator just as a pi. The r was given as 2.00 centimeters in radius. You square that, and then the h is 6.00 centimeters tall. Put that in the formula, you're going to get a volume. But that volume is going to be in cubic centimeters. Ugh. You've got to convert that because you're using mass density. You've got to convert that to cubic meters. And you know how to do that. We did several conversions today. Okay? Convert the centimeters to meters and then cube them. It's going to wind up for 1,000,000 cubic centimeters is 1 cubic meter. Okay? So you've got that part. Well, it says aluminum, so go back to your, remember that table I was talking about? No, let me get my paper. I just lost it. In place. Go back in chapter 12 to that table on page 330 and find aluminum, and that's the very first one, and it gives you the mass density is 2,700 kilograms per cubic meter. Okay? So with all that in place, you calculated your volume in cubic meter, which is going to be a very small number. The mass density, which is a pretty large number, you have to multiply the mass density times volume. That will give you the mass in kilograms. But it's asked how much it weighed. So then you have to multiply that by acceleration due to gravity to get the weight in newtons. So it's a multi-step problem. Okay. What's that? Not quite. Or you got to say again? No, you're not using joules. Okay, when you said 12, did you do 6 times 2? No. Obviously, it didn't like that. It turned the light off. Okay. What you do is square the 2 because it's r squared. Okay, so that makes it 4. Times 6 would be 24, but then you have to multiply it by pi. That's going to be about 3, so that you're going to have something in the neighborhood of, I don't know, 24 times 3. That would be about 72 or something like that. Whatever it turns out to be. That's the volume. You have to convert that to cubic meters. Boy, turned in already. Okay. And then, after you do that, you have to convert it to cubic meters, and then you calculate the mass from your density formula, using the mass density in this table on page 330. And then once you found the mass, multiply it by acceleration due to gravity, which is 9.8 meters per second squared. and that will give you the weight. So it's a multi-step problem.
Can I ask you something?
Sure.
About my test.
Okay.
Because I call myself looking it up. Do you remember that one on number 10 right here? When I kept saying, well, I even wrote it, but then I kept saying, is 0 going up and 0 coming down? But it was actually 123 going up and 123 going down.
All right.
For number 10.
Mm-hmm.
You remember when I kept saying the 0, when I kept saying if it goes up, it has 0 frequency. And
Okay, wait. No.
I know that it would have been 123, but I kept telling you that it was 0 going up and 0 coming down.
Okay.
So,
All right. The velocity at the highest point, you got absolutely right. Because as it's going up, it's slowing down. And when it stops, the velocity is 0. And then it starts coming down. Okay? So at the very top, the velocity is 0. But then it's picking up speed all the way down. So at the bottom, it's going just as fast as it did when you threw it up.
see, I did that part right in here.
Right there, you got it.
And see, when I told you it would have been going up, and then when it came down, it still would have been that. That's why I put this in that, because 0 going up and 0 coming down.
Right, okay.
So
No.
I just got frustrated,
Okay.
you know, when I looked at it, because I know I put it right on my paper. Then I turned around and then did the zeros, because that's what I kept saying in class.
Right.
Is 0 going up, 0 coming down.
Okay. When you have it at the bottom and you throw it up, it told you it's 123 when you throw it up.
Right.
So at the bottom, that's its velocity going up.
Right.
Okay. That's the velocity going up. But as it goes up, it's losing speed, right? Slowing down. And when it reaches the very top, right before it falls, its velocity is 0 because it's no longer going up or coming down. At that instant when it stopped, its velocity is 0. And then when it starts falling back down, it's picking up speed again and picking up speed. If you caught that ball that you threw straight up in the air and caught it, it's going at a speed. It's not going at 0. If it was going at 0, you could just let it sit there and it just hang right there. And you know it wouldn't do that. It would be 123 coming down. No. Yeah.
I you know, it just took me by surprise because I kept saying that, but you know, I didn't round it. Was I supposed to round it?
Which?
Right here.
No, that's fine. I said, okay, that's fine.
Okay, and then right here on number 9, that's why I like to write my problems out. You see where I square rooted right here? What was I supposed to do right here?
Okay. If you go get your calculator, and we'll watch what it does. Okay. Now, I don't know what order your calculator does things.
Okay.
Okay.
Like this.
Okay, well, let's try that. The 2 times 32.2 times 45 equal. Okay. And so you get 53.66 or 0.83.
Okay.
See? And that was the right answer, 0.83. They put 0.81. It doesn't matter. It's close enough. So you see, I don't know. You entered the numbers right here, but you put your answer wrong. I don't know why. I mean, I don't know. Yeah.
I was talking.
Okay.
And then this one right here, the jewel. I just knew that one was right because it's
which
half.
one? Yeah.
See, half of that.
Okay, wait. Find the kinetic energy of a 310 kilogram wrecking ball moving at 4 meters per second. Okay? And so let's do it. 310.
That'll be 155.
Okay, 155 if you take half of it first, times 4 squared. I bet you forgot to square it.
Times.
No, not square root. Okay, square. That's the key right there. It's, what do you say, 155 times 4, and then squared, that key right there, equal 2480, and they round that to 2500.
Okay, you see what I did? I divided that again.
Yeah, but you see, you had already done half of this. So once you did half of that, don't half it again. And that's exactly what you did. That's why you came out exactly half the answer that you should have gotten. Okay. Well, no, not quite. You halved it twice. So yeah.
I just got to be careful.
Yeah.
And then
I gave you half credit for all those.
This right here.
Okay.
This right here.
Okay.
Go to number 7.
Which one? 6? 7. Okay. All right. Okay. Let's see what the problem is. Pump capable. 5 watts. Okay, 5,000 watts. How many liters of water per minute can be lifted the distance of this? So you got your distance right. So your okay, first your formula here is wrong. That's energy is equal to mgh, not power. Okay. Energy is mgh. Power is energy per unit time. Okay? And so what you're looking for is so energy is equal to mgh. Power is equal to energy divided by time. So you're going to have to, okay. So therefore, you can either multiply the time by the energy. Now, let's see, the time wasn't in the problem though, was it? No, liters per minute. So that's what you wanted. Now, remember we did one like this in the thing.
That's what I was going by.
Yeah. Okay. A liter of water has a mass of 1 kilogram. So if you, this mass here in kilograms, that would be the same as liters. Okay. So your 5,000 watts is the same as 5,000 joules per second. Right?
Okay.
That's what a watt is. Well, a joule is, and that's what you wrote here, that would be 5,000 kilogram meters squared per second squared per second. Okay. What you're looking for is how many kilograms per second, because that's going to be the same as liters per second. So what you need to do is basically
see this right here on that page. You said 9.8 times 9.8 square m square times that 25, and
okay,
then
but where was the 25? Oh, 25
right
meters. Okay,
25 meters.
Yeah, so there's your 25 meters. So these, okay. This is your energy. What you have here, this is your energy. This is meters squared per second squared. No, you don't have your kilograms in there yet, so it's not the energy. Meter squared per second squared. This is what you need to divide into this. So that's, I don't know if that's what you're saying here, but if you take this number here, yeah, the GH, yeah, if that's an H there, that GH divide that into the power, that would leave you exactly kilograms per second, which you could then say is that, so if you take your 5,000, divide by this number here, 25 times 9.8.
And he gave me that.
Okay, no, I don't think so. Let's try it. 5,000. Okay. Okay. Well, let's first multiply these things together. Oh, and that's what you got here?
Yes.
Okay. This is your GH then. Your GH is this here. That's meters squared per second squared. Okay?
245.
Okay, well, yeah, we'll count that. 245. 5,000 divided by that.
That's not right.
No,
I
yeah, you
should've
did
put
it the other way. 5,000 divided by 245. Okay. But, okay. It's not watts, okay, for sure. But it's supposed to, oh, here it is, okay.
So,
Which one are we talking about? Oh, this one, number 7.
mm-hmm.
Okay. Oh. Here's the only place it missed it. This says liters per minute. This is liters per second.
Oh.
This is in liters per second. Multiply that by 60 times 60. You divide it by 60.
Oh, good. I got to do all of it over again.
No, just do 20.4 multiplied times 60. 60 equal 1224. And because you only have, where is it? You only have 2 significant digits there, 2 there. You round that to 1200.
Oh, okay.
See, that's the only thing you had wrong.
But wait a minute. You can't round that to 1,200.
Yes, you can. You count out. You got 2 significant digits. Count 2. 1, 2. That is
Okay.
less than 5, so you make that a 0 and that a 0.
Oh, okay.
Yeah.
I'm rounding up instead of rounding
Yeah.
down.
Okay. So that was, what you had was liters per minute.
Okay.
Okay? No, you had liters per second.
Second.
Yeah. You had liters per second. And if you had put that down as 20.4 liters per second, then I would have known you were on the right track, and that would have been, but you put down watts, and I thought, ugh, you're asking for that. I didn't see your work. I didn't go back and look at it. So, but yeah, that's the only place you missed that. All you had to do was multiply this by 60 seconds per minute. And the seconds go out, and that gives you liters per minute. That's exactly where that came from.
Okay, I just got to be careful.
Yeah, you're doing well.
No, but I need to make 90s. I can't do 75s anymore.
You can't what?
I can't do 75s.
Oh,
I got to stay
well, you didn't
up.
do 75 the first time, so you're going to do okay. I bet
Just
you.
got to make my next test count high.
Yeah. I could drop your lowest score, so that one may be gone anyway. Yeah.
All right.
All right.
See, I'm over here sniffling. I'm like, what is this?
Yeah.
I know I worked it. I stayed up and I get it.
Yeah, you will.
These are 3 questions I got to do.
Okay. I've got to find.
Oh, I have a pinched nerve in my back.
I knew you did.
And they want to, she said she don't want to do surgery. She want me to go to therapy
Uh-huh.
and try and work that out.